Hello everyone, and welcome to Recitation with Sohail. Today we're going to do problem 31 from section 2.2 of the 10th edition of Boyce and DiPrima. So this time we just want to find the general solution to the differential equation given in equation 1, which is that dy over dx is equal to x squared plus xy plus y squared, all divided by x squared. Now we see that this is not a linear differential equation, which is a shame because that's a class that we know how to solve and it's well studied. It's also not a separable differential equation, which is unfortunate because that's another class we know how to handle. And I won't show you that it's not separable, but you can try to fiddle around with it yourself and you can try to separate variables, and most likely you won't succeed. But this is part of another class of differential equation that we still know how to solve. This is a homogeneous differential equation. So it's a differential equation where we're going to make a substitution and convert it into a separable differential equation, from which point we can separate the variables and solve the equation in a manner similar to that which we did in problem 17 from section 2.2. So homogeneous differential equation is just a differential equation of the form dy over dx equals a homogeneous function of x and y. So what is a homogeneous function of x and y? Well, we're going to give it a name. This function we have, this x squared plus xy plus y squared over x squared, I'm going to call it capital F of x comma y. So really, I'm giving it the name capital F, and I'm specifying that the variables are x and y. Now, the differential equation dy over dx equals capital F of x comma y is a homogeneous equation if the function capital F is a homogeneous function. And what does it mean for the function f to be homogeneous? Well, homogeneity is the property here that we have in pink, namely that if I pick any real number c, then f of cx comma cy is equal to f of x comma y. It's homogeneous because when I scale the input by some constant c, the answer doesn't change. It stays the same. Invariant under scaling. So to check that, this equation 1 is a homogeneous equation, like I told you it was, we just need to check that the function f, which I've written here in equation 2, is actually a homogeneous function. And that's just a calculation that I've written out for you in lines 3 and 4. So we see that if I just plug in cx and cy into my definition of f, then I get cx squared plus cx times cy plus cy squared, all divided by cx squared. I'll just expand everything to get rid of the parentheses to get c squared x squared plus c squared xy plus c squared y squared, all divided by c squared times x squared. And then we can cancel out a factor of c squared from the numerator and denominator. And after we cancel it out, we see that what's left is indeed just capital F of x comma y, which is what we want. So f is indeed a homogeneous function, which means that equation 1 is indeed a homogeneous differential equation. And note that so far we haven't really done any calculus. Checking that the function is homogeneous, you don't need to take any derivatives or integrals, just some algebraic manipulations. Or really just checking some algebraic identities. And now that we've checked them and we know that the function f is homogeneous, we make the following substitution. The substitution of v is equal to y over x. So this is the substitution that we're always going to make for a homogeneous differential equation. And it will always convert a homogeneous differential equation into a separable differential equation, which is why we like the substitution. Now, before we actually do the substitution, we have to remember that this isn't an ordinary equation. This is a differential equation. So we need to substitute not just v, but we're going to need to know what v prime is, because the derivative is going to show up as well. So we'll go ahead and prepare that so we can have it in substitution as well. So I take a derivative of v, just have to use the quotient rule. And when I use the quotient rule, I should get y prime over x minus y over x squared. And then y over x squared is the same as v over x. So I'm keeping all of the x's when I do this substitution. X is the independent variable. I don't need to change that, but I'm trying to get rid of the y's. I'm trying to replace all of the y's with v's and v primes. So that's why this y over x squared, I replaced it by v over x. And then in this equation, if I add v over x to both sides, multiply by x afterwards, I end up with equation 6, which says that x times v prime plus v equals y prime. So now I can go ahead and replace all of the y's, or really the y over x's, using this equation, v equals y over x. And I can get rid of the y prime by replacing it with x times v prime plus v. Now, I know I just said we want to get rid of the y's, and here I'm replacing y over x, not y. But we'll see how this works out in just a moment. So first, the left-hand side, here was the original differential equation, right? This is what we started with. And I told you in the definition of homogeneous equation, the left-hand side is always going to be y prime. So I can always just replace that y prime with x times v prime plus v. And that just gets rid of the y prime every time. It gives me x, which I'm okay with, and gives me v prime and v, which I anticipated. So that's all good. Now, this is the part where we're going to make use of the homogeneity, right? Because technically, everything I've said so far, this replacing y prime with x v prime plus v, you can always do that if you want to. You can always just define v to be y over x, and then determine that y prime is going to be x v prime plus v, and make that substitution. But the reason this is a useful substitution is because of the homogeneity, as we're about to see. So because we calculated that the right-hand side, this x squared plus xy plus y squared, all divided by x squared, is a homogeneous function, that means that we will be able to rewrite the right-hand side as a function only of v, as opposed to a function of x and y. Now, how we do that is going to vary on a case-by-case basis, but it will be possible to do no matter what, because we checked that it is homogeneous. So in this particular situation, I'm just going to break up the fraction into 3 separate pieces. I'm going to simplify, cancel out as many x's as I can, and I'm going to note that y squared over x squared is the same as y over x squared. And then I see that the right-hand side simplifies to 1 plus v squared. And then to simplify this differential equation, I can just subtract v from both sides. So I can cancel out this v with this v. And what's left is equation 9, which says that x times v prime equals 1 plus v squared. And sure enough, we see that this is a separable differential equation. All that I had to do was to take this 1 plus v squared, divide by that, and one other small step, I just had to take this x and divide by that as well. And then as I told you in my previous video about problem 17, I like to write the v prime as dv over dx to make this final adjustment, but that's technically optional. I wouldn't worry too much about that detail. So yeah, here, here, and here. And we can also just notice here that even though I'm showing you a specific instance of a homogeneous equation, what's always going to happen for any homogeneous equation is this left-hand side is going to turn into x v prime plus v. And then the right-hand side, I told you, it's always going to turn into a function of v. That's why we check for homogeneity. So anytime we have a function of v, I can subtract this v from the left-hand side to the right-hand side. It might not always cancel. We got lucky that it canceled, but you can still subtract the v over. And when you do that, the right-hand side is going to be a function entirely of v. So you can just divide by it, and you can divide by this x, and you can always separate the variables. So that's just a little abstract reasoning to see why this technique will work for any homogeneous equation. Nonetheless, returning to equation 10, which is where we've gotten so far, we see that we have separated the variables. So we can go ahead and integrate each side. And then we know that the antiderivative of dv, or 1 over 1 plus v squared, is tan inverse of v. Antiderivative of 1 over x is natural log of x. And I put both constants of integration onto one side, so I just have this plus c. Then the problem started off being a problem about x and y, so I want my solution to be with x and y. So I'm going to replace this v with y over x once again to get rid of the v that I introduced, bring it back to y and x. Then this is an implicit solution. Equation 13 implicitly solves equation 1 because there's no derivatives in it. But luckily, we can go further. We can get the explicit solution. So I can take the tangent of both sides to cancel out the tan inverse. And I get that y over x is equal to tangent of natural log of x plus c. Then I just multiply by x, and I get my explicit solution of y in terms of x. And we didn't have any initial values, so that's why we keep the c, and we get the general solution. So now that we have the general solution, the next question that we want to ask is, what are some intervals on which the solution is valid? Now, this is a little tricky because we don't have the initial conditions to specify an interval, but we can still try to determine separate intervals on which the solution exists. And then if we were given an initial condition, we could pick out one of those intervals. And part of the reason I want to do this with you guys for this problem is that this is actually a pretty hard problem to find the intervals on which the solution exists. There's a lot of steps to it. So I think it's good to see how you do it for a hard problem, and then you'll be more confident when you come across easier problems. So for starters, we need the solution, y, to be defined, right? And there's a couple problems here. There's the natural log, and there's the tangent. So we see that a tangent requires the input to be in between two odd multiples of pi over 2, right? This input, this natural log of x plus c, has to be in between two multiples of pi, because that's where tangent is defined. And in case you forgot, let's just look at a quick graph that makes it very obvious as to why this is the case. All right, here's the graph of tangent of x. So these red parts right? We have these blue asymptotes, that's where the problems are. So all of these good chunks are occurring between two consecutive odd multiples of pi over 2. Right here, it's -1 times pi over 2 to +1 times pi over 2, and then +1 times pi over 2 to +3 times pi over 2. So that's where this came from. Now I can subtract the constant to the other side, and that's where I get the next half of equation 16. And then to undo the natural log, I take an exponential. So I apply e to both sides, and because e to the x, the exponential is an increasing function, I don't have to switch the order of the interval. So I can just take e to the first part, put that in the beginning, and e to the second part, put that at the end, because e is increasing. So we know that a connected interval on which the solution exists is of this form, of the form e to the 2n minus 1 over 2 times pi minus c up to e to the 2n plus 1 over 2 times pi minus c, where n is some integer. And I know this is a bit abstract, so I should specify the integer n and the constant c will both be determined by the initial value when you are given an initial value. So if we're given an initial value, for example, y of 0 equals 0, actually, excuse me, I can't put in x equals 0 for the initial value, because then this natural log of x over here would be undefined. So if we had a condition like y of 1 equals 0, then I could plug in x equals 1 into the ln and here, and I could plug in y equals 0 and use that to solve for some value of c. And then once I have the value of c, I know that the value of n will be determined by 1, right? Because I said y of 1 equals 0. So I want to pick the n such that 1 is inside of this peach interval, inside of the interval 2n minus 1 over 2 times pi up to 2n plus 1 over 2 times pi. Or namely, if I pick the y of 1, so x equals 1, I want to pick the n that corresponds to this part of the tangent function. So point being, you can determine n and c if you're given initial conditions. So that's all I have to say for problem 31. Thanks for tuning in, and hopefully, if you like the video, give it a like and subscribe.